have successfully written the Fibonacci sequence calculator inside of assembly using recursion.
Assembly recursion, layer.
Hi everyone, thanks for watching laurieWIRED, and in this video we're going to be computing the Fibonacci sequence in assembly on a Raspberry Pi. Now we have two methods that we can use for computing the Fibonacci sequence. We can either use an iterative approach or we can use a recursive approach. Now the recursive approach involves the function calling itself with smaller instances of the same problem. Now just a quick reminder that inside of the Fibonacci sequence, each number is equal to the sum of the previous two terms inside of the sequence itself. So let's get right into it and let's start writing some assembly. Now I'm going to open up my connection to my Raspberry Pi, and I've gone ahead and added some files already inside of here. What I have is a visualizer that is written in Python that's going to be listening to the output that we're creating from inside of our fib.s file. Now this is going to contain our ARM v7 assembly code that we're going to be writing today. And then at the end, we're going to run our visualizer and see if we were successfully able to compute the Fibonacci numbers from inside of our ARM v7 assembly program. So let's take a look at our program and let's see what we need to add to start computing these numbers. So I'm going to open up fib.s. And if we take a look at this file, I have some stub code already written. All this is going to do is it's going to take the output that we're writing and it's going to add this to a file. And our visualizer is going to be continuously listening to this file and trying to visualize the Fibonacci numbers as we're computing them. But all of the actual compute on the back end is going to be performed inside of our assembly. So all of our recursive code is going to be inside of this file. Now we have our print function, our file writing function, our main function is already all written for us. So what we want to focus on is going to be this Fibonacci function that we have defined right here. Now if you take a look at our stub code, you can see all we're doing is just simply returning the immediate value 42 and passing that into our R0 register, which is going to be the return value of the function. And then if we look at our main function, it's going to be printing that Fibonacci number to a file that's going to be visualized by our Python script. But I don't actually want to just return the immediate value 42. I actually want to do the computation of the Fibonacci sequence inside of this function. So let's go ahead and replace this code with our actual function calls. So I'm going to get rid of this code. And let's start thinking about how we want to begin our computation of the Fibonacci numbers. So I'm going to add a new line here. And let's pause and think about this, how we would write this in a C program if we were trying to compute the Fibonacci sequence recursively. So we would start with our base case, and then we would continue on with our recursive case. So our base case would test and see if n is going to be less than or equal to 1. Now we're trying to find the nth Fibonacci number here. So if n is less than or equal to 1, we're going to want to return out of the function and simply return the value of n itself, because that means that we've broken down all of our instances into the smallest instance of this, and this is going to be the last case that is going to run. So let's just add a comment in here and let's talk about our base case and kind of define that for ourselves before we actually write the assembly portion. So I'm going to label this base case. Now let's add a comment in here that's going to check and see if n, which remember we're trying to find the nth Fibonacci number. So if n is less than or equal to 1, then we're just going to return n itself. So that's how we would do it if we were writing this in C. So let's move on to our recursive case. And let's kind of define what we want to happen here when we want to perform the recursion itself. So I'm going to label this recursive case. Now, if we have our recursive case, what we want to do is sum the previous two Fibonacci numbers. So how would we do that? We would want to try and find Fibonacci of n minus 1 if we're currently on the nth term, and then we would want to find Fibonacci of n minus 2 as well, and then sum those together. So let's kind of define this inside of a comment before we write our actual recursive case in assembly. So I'm going to do Fibonacci of n minus 1, and then we want to add these two terms together, plus Fibonacci of n minus 2. So this is kind of our structural outline for how we're going to write our code. So now let's get to the exciting part, and let's just start writing the assembly itself. I'm going to begin with my base case here. So now our n value is going to be passed in our R0 register, since this is the first argument to the Fibonacci function that we're calling over here. And remember, the R0 register is also going to hold our return value, so we're going to have a lot of use for the R0 register inside of this function. So what we want to do, since R0 is containing the current value of n, we're going to have a compare. So CMP R0, which is really the n value, we're going to compare to the immediate value 1, and then if n is less than or equal to 1, so branch less than or equal to, we're just going to go ahead and exit out of this Fibonacci function. So we can go jump over to the label end fib that is down here. That's simply going to pop off the current value on the stack, which is going to be the value of the link register, and then put that into our program counter, so we're going to effectively jump out of this function. So we're just going to branch over to that label once we've finished this base case. So branch less than or equal to 1, we'll jump to end fib. Now we don't need to do anything with the R0 register since it contains the value n, and what we're doing is we're just going to be returning the actual value n if we enter this base case. So let me add that in my comment as well so it's clear. So we're just going to return n itself. So now let's move on to our recursive case. So our current value of n is inside of our R0 register, but what we want to do is we want to compute the value n minus 1. So I think I'm going to push the R0 register to the stack so that we don't lose that original n value while we're performing these additional computations. So I'm going to go ahead and do push, and we'll push our R0 register. So this is effectively saving the current value of n to the stack, and then we can do whatever we want with that R0 register because we can always restore the state after we finish our computation. So what I'm going to do is I'm going to do sub, we'll do R0 as the destination register, R0 as the first operand, which is going to be the value of n, and then we want to get n minus 1. So let's subtract the immediate value 1 from that. So now we've effectively found n minus 1. So we can branch into our Fibonacci function yet again. So this is the recursive portion of this, so we're effectively calling ourself from inside of this same function. So I'm going to do branch and link over to Fibonacci. Now this R0 register, again, is containing the argument passed to that Fibonacci function, so we're passing the new value of n, which is going to be the smaller subset, into this Fibonacci method. Now we have actually called our first instance of our Fibonacci method inside of our own Fibonacci method. So we've computed Fibonacci of n minus 1. But we have one more call that we need to make to be able to add Fibonacci of n minus 1 with Fibonacci of n minus 2. So we now need to actually compute the Fibonacci of n minus 2 portion. So let's move on and let's add some code here. Now, first things first, we're going to want to save the return value of this Fibonacci of n minus 1. And this is going to be stored in our R0 register, which remember we're using multiple times as both the argument as well as the return value. So let's go ahead and push our R0 to the stack. But first I want to again get my original value of n because we're about to compute n minus 2. So I'm going to use one more register for this so we can store multiple values. I'm going to pop the original value of n, which we pushed up here, into our R1 register. So let's do pop R1, so this is the original n value once more, and then let's push our n minus 1 Fibonacci number to the stack so we can save that to give us time to compute Fibonacci of n minus 2. So once more I'm going to do push R0, since R0 was the return value of this Fibonacci of n minus 1 call. So now both of those are saved. We have our original n value inside of R1, and then we have our original n-1 value put inside of R0 on the stack temporarily. So let's move on. Now let's calculate our Fibonacci of n-2. So I'm going to do sub, and we're going to put the destination register as R0, which is again going to hold our argument to our next Fibonacci call. And then we have our original n value inside of this R1 register that we popped from the stack. So that's going to be our parameter. And then we need our immediate value of 2 to be subtracted from that original n value. So I'm going to do the immediate value 2. And now, once more, we can actually call our Fibonacci function inside of our Fibonacci function. So we'll do branch with link, and then call Fibonacci one more time. And now we've successfully computed Fibonacci of n-1 and Fibonacci of n-2. So what we need to do is we need to sum these two values together so that we can return this from the function. And then we will have successfully completed our recursive case as well as our base case. So now we want to get our previous two terms, the n-1 and the n-2, and let's add those together. And we have our n-1 value was already pushed to the stack up here. So let's pop that one more time, and I'm going to pick on our R1 register again. So we'll do pop into R1. And then if you notice, we called our Fibonacci method up here, so that return value of Fibonacci of n-2 is already going to be put inside of the R0 register. So let's go up here and let's do add. And we'll make the destination R0, since remember that's going to be our return value for the entire Fibonacci function. So do R0, and then we have R0, which was the n-2 value that's already inside of there. And then the R1 register that we just popped our n-1 value from the stack into the R1 register. So now that looks good. We've got our base case up here. We've got our recursive case down here that are going to be computing the previous two Fibonacci numbers. And then once we finish our recursive case, it's just going to naturally keep going through the instructions and get to the end fib. And we have already put our added values inside of the R0 register, which is going to be the return value for the function. So we should be pretty much good to go here. So let's assemble this program and see if we made any mistakes. So I'm going to get out of here, and we'll do save this. Looks good. And I'm using ARM v7 assembly right now, so I'm going to assemble this program. And the command is going to be ARM Linux GNU EABI assemble. And we need our assembly source file, of course. So do fib.s. And then we'll make our object file, just name it fib.o. Looks good. No errors with the assembler, which is a good sign. So now let's generate our executable. I'm going to do ARM Linux GNU EABI GCC. And then I'm going to statically link this since I'm calling some different C libraries from inside of my fib.s file. So this is just a little simpler for our case to add all of those libraries inside of the binary itself. So I'm going to do dash static, and then we'll pass it our fib.o object file that we generated. And then we'll make our executable. Looks good. And we have our executable generated right here. So let me just make sure that looks good. File. And sure enough, we have our 32-bit ELF binary that contains our ARM v7 assembly code. Now let's go ahead and run this and visualize our output and make sure we have correctly recursively computed the Fibonacci sequence inside of assembly. Now, if you would like to follow along, I have made all of the code available inside of my GitHub repository for assembly challenges under the Fibonacci folder. We have our fib.py, which is our visualizer, runfib.sh, which is going to trigger the fib.py and fib.s. And if you would like to fill in your own version of the Fibonacci calculator, you can use this Fibonacci fillable, which is going to not contain all of the code inside of the Fibonacci function, or you can just run my code, which is going to be fib.s, which is already completed for you. Now let's go ahead and use the assembly code that we wrote and visualize our Fibonacci sequence using our Python script. Now I have a bash script on here that's going to trigger the Python code, and that is going to be reading the Fibonacci sequence that we've generated on the back end inside of our assembly program, and it's going to repeatedly calculate the value of n until we get up to the n that we have successfully selected. So I'm going to do /run, and let's just select the 16th Fibonacci number and let's compute that. So now let's enter and watch our visualizer. And here are all of the different Fibonacci numbers that it's calculating. And it looks like 987 is the 16th Fibonacci number, and we have successfully written the Fibonacci sequence calculator inside of assembly using recursion. So thanks so much for watching laurieWIRED, everyone, and I'll catch you in the next video. Okay, so for this one, ooh, I like this one. Oh yeah, yellow, here we go. Okay. Let's go.